Alright, what I want to look at here is mathematical combining of waves. Now, I think in one of my other videos, I forget which one, probably the one on standing waves, we looked at the format for a wave being like this. We've got two independent variables, the t and the x. So that's because the wave actually moves in time. So you could draw a graph of it at a fixed place and see what happens as it changes in time, or you could draw a graph of it at a fixed time and look at it at different places. Kx is wave number. K equals 2 pi over wavelength. So it actually gives you how many radians per meter it is. So if the wavelength was 2 pi meters, then the wave number would be 2 pi radians and 2 pi meters. So that would be 1. So you can see when you've got a small wavelength, you get a lot of radians in a meter. And when you've got really big wavelengths like radio waves, you don't get many radians in 1 meter. So that gives you gives you the size of the wave. So if we're going to actually combine constructively two waves with the same frequency, so we could call this one y1 and we'll call this one y2. We can give them the same amplitude, but same amplitude, same frequency, same wave number, so therefore same speed. But we've just got a phase difference with them. We'll call that phase difference theta. Now what we can do then is combine them, y1 plus y2, right? And we could make a substitution there, because we know that the sine of A plus the sine of B is equal to 2 times the cos A minus B over 2 times the sine of A plus B over 2. That's our trigonometric identities, remember? And if we make a little substitution there, A equals kx minus omega t, and we make another substitution, B equals kx minus omega t minus the phase difference, then we can solve that pretty reasonably. We can just substitute them in, and then we end up with this equation, which is what we're looking for, 2a naught cos phase difference over 2 times the sine of kx minus omega t minus phase difference over 2. So what's that telling us? Okay, that's telling us that the phase difference has a lot to do with how these two waves with the same wavelength and same frequency but slightly out of phase are going to look. It's going to produce one wave, right? Now that wave is going to have the same frequency, it's going to have the same wave number, all right? So it's going to be pretty much the same wave, but its amplitude is going to be modulated and its phase is going to be different, right? Now if the two waves originally were 45 degrees out of phase, then this one compared to the original will be in between, 45 degrees divided by 2. Now if we've got a phase difference of pi, which is half a wavelength, right, then we can see what's going to happen. Let's look at this end for a start. If we look at the cos graph, right, cos graph basically goes like that, from 0 to 90 degrees. Now what happens to a cos when it becomes 90? And 90 in radians is pi over 2. So a cos goes to 0 when the angle equals pi over 2, or 90 degrees. So if the phase difference in the two original waves is pi, then this becomes pi over 2, which becomes 0. So that's basically telling us that when we've got two waves 180 degrees out of phase, then this is telling us that they will totally cancel out. Now if they're 0, if the phase difference is 0, then that's the cos of 0, which is 1. Then 0 over 2, they will have the same frequency, same wave number, and their amplitude will be twice the original wave. So this is telling us that two waves totally in phase will have an amplitude twice the original. So this formula tells us everything about two waves superpositioning or constructively interfering or destructively interfering or anything in between. This is the formula. Quite simple, really.